All right, let's dive into a really powerful mathematical tool that helps us understand our world. We're talking about the separation strategy, a way to solve the very equations that describe change.
So, how can we predict the future? I mean, think about it. How fast does a population actually grow? Or how long until your coffee is just lukewarm? These are all questions about change over time. And to answer them, we need more than just a good guess. We need a blueprint.
And that's because we live in a world that is constantly in motion.
You know, a picture is great, but it's just a snapshot, right? One single moment in time. What we really want to know is the story between those snapshots. How did we get here and where are we going next? For that, we need a whole new language.
And that special language? Well, that's what differential equations are. It's basically how mathematicians write down the rules of how things change.
Now, don't let the name intimidate you. A first-order differential equation is actually a pretty simple idea. It just connects some quantity, let's call it y, to its rate of change, its speed, basically, at that very instant. The equation is just saying that how fast something is changing depends on what its value is right now and maybe what else is going on around it.
And yeah, the official definition can sound a little textbooky, but this is the core concept. It's this language that lets us model everything from the orbit of a planet to how fast a chemical reaction happens. It's the language of a world in motion.
Okay, so within this huge topic, we're going to zoom in on a special kind, a really useful kind, called a separable equation. And the name pretty much gives the game away. You can literally pull apart the x stuff from the y stuff. The form is always some function of x multiplied by a function of y.
And because we can pull them apart, we have this incredibly elegant way to solve them. It honestly feels like a simple trick, but it unlocks the answers to some really complex problems.
So the strategy is like a four-step recipe. It's super logical. First, you just get the equation set up in that separable form. Second, and this is the key move, you get all the y terms on one side and all the x terms on the other. You separate them. Third, you integrate both sides. This is kind of like hitting rewind on the rate of change to find the original function. And finally, step 4, you just do a little algebra to solve for y, and boom, you've got your answer.
Okay, pop quiz. Take a look at this equation. What do you think? Is it separable? Can you actually write it as some function of x times a function of y?
If you said no, you are absolutely right. That little plus sign in the middle is the culprit. Because the terms are added, there's just no way to factor them into that f of x times g of y form that we need. So our cool separation trick, well, it's not going to work here.
All right, round 2. How about this one? Does this equation fit the pattern we're looking for?
Yes, this one is a perfect match. See, we've got a function of x, that x squared plus 6, and it's multiplied by a function of y, the y minus 2. This is exactly what we're looking for. It's a perfect candidate for our separation strategy.
So this is all great. We can spot them and we have a plan to solve them. But this isn't just a math exercise, right? This is how we actually get to solve those real-world riddles that we started with.
Now, take a look at this. On the left, we've got the model for natural growth, like a population. On the right, Newton's law of cooling, which describes your cooling coffee. These two things seem totally unrelated, right? But just look at the structure of those equations. See the similarity? They are both separable.
And here's the real kicker. The exact same 4-step strategy we just talked about can solve both of them. That is the real power of this whole thing, recognizing that the same mathematical patterns can show up in completely different parts of the world.
Okay, but there is one last really important question we have to ask. We've found a solution, but how do we know for sure that it's the only solution?
I mean, think about it. If there were a bunch of different possible futures that could all come from the same starting point, our model wouldn't be very useful for making predictions, would it? We need to know if our answer is the answer.
This is where a big idea called the existence and uniqueness theorem comes in. But honestly, the gist of it is pretty simple. It says that as long as your rate of change formula is well-behaved, no sudden jumps, breaks, or other weirdness near your starting point, then the math guarantees two things. 1, that a solution path actually exists, and 2, that it's the only one.
So in plain English, this is our guarantee that the future is predictable, at least mathematically. It gives us the confidence that the path we calculate, whether it's for a growing population or a cooling cup of tea, is the one and only path it can possibly take. It means our model is reliable. So, now you have the tool.
You can see the underlying structure of change, and you have a strategy to map out its future. So I'll leave you with this question. What's some process of change happening in your world that you'd want to model first?